Hello all. In today's session, let us discuss next models which are used to perform object detections which are different from that of the previous models what we have discussed like RCNN, fast RCNN and faster RCNN. So we will be discussing single shot detectors and you only look once models. Starting with SSD. The main aim of SSD is to improve the speed by eliminating the need for region proposal networks what we have studied for RCNN network. And that aim of increasing the accuracy and speed will be done by making use of multi-scale features as well as default boxes. It was released in 2016 by YOLO with 74% of mean absolute precision at 59 frames per second. Unlike RCNN, SSD and YOLO, both these models will perform processing of image or object detection only in a single pass. Hence, you call it as SSD. In RCNN, what do you have is it generates region proposals in one flow, and in the second pass, it will generate the classification of that particular target given in the image. But in SSD, the process is completely different. Both these region proposal generation as well as classification will be carried out in only one forward pass. Hence, you call it as single pass. So, these both models are called as single pass models. SSD is single shot detector and YOLO represents you only look once. So, the process is very simple here. Once the features are generated through a pre-trained model, the objectness score for each bounding box will be predicted. That is, for each feature map, multiple bounding box at different scales. As I told you, for example, we talk about this feature map. At this feature map, an anchor point is formed, and depending upon different aspect ratios, you generate different n number of anchor boxes, also called as predefined boxes. For example, consider 3 bounding boxes or 3 anchor boxes are generated. So in SSD, for each feature map location, SSD will predict what? Multiple bounding boxes at different scales and aspect ratios for each feature map location. For each bounding box, for example, as I have 3, each bounding box model will assign what? The objective score as well as the class score. So as I have 3 bounding boxes, for each bounding box I will have objectness score which represents object is contained in that or not, as well as class scores, that is the probability for each object class will be generated. In that way I will have 6 different outputs, 2 for each bounding box. And objectness score represents what? Object is contained with that within that anchor box or not. So, to generate these objectness score, SSD makes use of an ML algorithm called as logistic regression to compute the objectness score. So, it is nothing but a binary score which generates 0 and 1 based on the threshold value. Hope you remember. This is the logistic regression. This is my threshold value. Values beyond this belong to class 1 or class 1 here, and values below this threshold belongs to class 0, and this class 0 and 1 represents what? Object is contained which is foreground and object is not contained which is background. And its objectness score will be calculated by using what? By using IOU. All this we have discussed in the previous sessions. Intersection over union, taking some threshold value, for example 0.5. If objectness score is beyond this threshold value, then it is a good match, that is object is present, and if it is less than 0.5, no object, that is background, will be predicted. This is what happens in SSD. Coming to the architecture, these are the 3 main parts. You have base network to extract the features. You have multi-scale feature layers as the second component, and the third component is non-maximum suppression. Coming to the base network, it starts with VGG16 which is used for feature extraction. You can see here that convolutional 5-3 layer as in the VGG architecture. Till here, VGG16 architecture is used for feature extraction, and these 2 fully connected layers are connected here, FC6 and FC7. These are used to preserve the spatial features which are extracted from this VGG16. And you can see here these are the extra convolutional layers which are added up, which performs 2 tasks, that is classification as well as finding the coordinates of the bounding box regression model. And outputs of all these are given here. And the total number of predictions what you can see is 8,732. That means for each 8,732 bounding boxes, SSD will predict class score as well as the coordinates of the bounding boxes. So this is the architecture where VGG16 is used as your baseline model here to generate or extract the features. Now what kind of output will be predicted here? For each feature, the network predicts the following: 4 values to represent the coordinates of the bounding box, 1 value for the objectness score either 0 or 1, and C which represents the probability of each class. So total of you have 5 plus C prediction values. 5 for what? 4 values for the coordinates and 1 value for the objectness score, and C represents the probability of each class as can be seen here. So each feature map is represented by XYWH which represents the coordinates, C1, C2, C3, C4 represents the probability of each class, and P represents the objectness score. Each feature map will be represented by these number of prediction values. Base network, as I already told, VGG16 will be used as base network to extract the features. And how this base network will extract the features? You can see in the image, anchor boxes are found here. Consider this following example. Suppose you have an image like this, and the network's job is to draw the bounding boxes around all the boards in the image. So the process is like this. For example, similar to the anchor concepts in RCNN, SSD will overlay grids here as seen here, which are nothing but the anchor boxes. In SSD, you call these anchors as priors. Now the base network will look at each of the bounding box and will separate the image. And when the network finds the bounding box that contains the board features, it will send its coordinates prediction and object classification to NMS layer, which will convert n number of bounding boxes to only one bounding box which has the highest probability. So this is SSD based network will look at the anchor boxes to find features of a board. Solid boxes indicate that the network has found the board feature, and dotted boxes will indicate that the no board features are present. Coming to the multi-scale features, these are the convolutional feature layers that are added to the end of base network. These layers will decrease in size progressively to allow the predictions of the detections at multiple scales. As you can see here, the base network may be able to detect the horse features in the background, but it may fail to detect the horse that is very close to the camera, because this bounding box is not covering the entire image of the horse which is close to the camera. To understand why, take a close look at the dotted bounding box and try to imagine this box along the context of the full image. So the camera, or we are unable to predict based on this bounding box that this is the image of the horse, because the images which are very close to the camera are large enough. Hence, for that case, we need large area of bounding boxes, that is large dimensions of the bounding boxes. Hence, we go for a method called as this multi-scale extraction, where larger feature maps are used to extract 8 by 8 are used to extract the small features, and 4 by 4 feature maps will be used to extract the large features. That is, larger feature maps will detect smaller images, and smaller feature maps will detect larger images, as can be seen in this boxes here. However, by using different convolutional layers that vary in size, we can use feature maps from different layers in the single network. So for prediction, we can consider the same effect while also sharing the parameters across all object scores. So hope you have understood why do we go for this multi-scale features, because we need to extract the images which are of larger size and close to the camera, which a small bounding box will not be able to predict that the object is contained in that or not. A CNN will reduce the spatial dimension gradually. The resolution of the feature map also decreases. As I already told, 4 by 4 feature maps are used for larger scale objects, and larger feature maps will be used to detect smaller objects. This can be visualized using this example here. So, multi-scale feature map will improve the network accuracy as well. Coming to the third component, non-maximum suppression, it will convert n number of bounding boxes to only one bounding box. This is what happens in SSD, where the classification and prediction of bounding box is done in one single forward pass. Coming to the second model called as you only look once. Now why do you call it as you only look once? Because the model will look only once at the image to predict all the detections. So it is a family of object detection network developed by Joseph Redman. We have different versions here. Version 1 was developed in 2016. Later in 2016, V2 was developed in 2018. Version 3 was developed. YOLO does not undergo the region proposal step like RCNN, same as in SSD. Instead, it will divide the image into grid, and each grid will generate different anchor boxes, and these anchor boxes objectness score of each anchor box will be calculated. If object is contained in that, those anchor box will be used for further analysis, and these are the final predictions after non-maximum suppression. So to detect the object of this building, this yellow bounding box is generated, blue is generated for detecting dog, and for detecting the car, pink bounding box are generated. So n number of bounding boxes are converted only into 3, as we have 3 targets here. So YOLO, what will it do? It will just split the given image into grid. Each grid will have n number of anchor boxes. Each anchor boxes will have two outputs, that is class label as well as the objectness score. Based on the objectness score, the highest probability objectness score bounding boxes or anchor boxes will be provided as input to NMS, which will finally give only one bounding box out of n number of bounding boxes. This is what happens in YOLO, you only look once. And the YOLO network splits the input image into these many number of cells, S by S cells. If the center of the ground truth bounding box falls into a cell, that cell is responsible for detecting the existence of that object. Each grid cell predicts the number of bounding boxes and their objectness score along with their class predictions as follows. So these are the outputs for each box. You will have coordinates of the bounding boxes X, Y, W and H. You will have the objectness score either 1 or 0, and then you will have the class prediction, k number of classes. So in third version, Redman decided to use sigmoid instead of softmax. The reason is that softmax imposes the assumption that each box has exactly only one class, which is often not the case. Hence in version 3, scientists have decided to use sigmoid instead of softmax. Coming to the architecture, you can see here, this is the architecture of version 3, YOLO version 3. Here, each grid is responsible for, this is the input image divided into S by S, that is 13 by 13 grid. Each grid will be responsible for predicting the attributes of the object whose center falls within the cell. So here center is what? Represented by a small red box. Here the center of the dog lies in this red cell. So this cell will predict the object probability. Red cell is responsible for predicting the attributes of the ground truth object because the object's center lies within this cell. So when you consider this red cell, you have prediction feature map with 3 centers here. Box 1, box 2 and box 3. These are the 3 bounding box prediction boxes which are generated, and for each bounding box you will have coordinates, objectness score and the probability of each class. Y multiplied by B, as you have 3 bounding boxes, you will generate X, Y, W, H, objectness score and bounding class probability for each bounding block. Like that you will have 3 different attributes of each bounding box will be generated. How many predictions will be done using this formula? S by S by phi b plus k, where S into S represents the number of grids the input image is divided, and B represents the number of bounding boxes, K represents the number of object classes. And why did I use here 5? Because as I told you, you will have 4 coordinates of the bounding box plus 1 objectness core, hence phi b plus k. For example, if you have input image is divided into 7 grids, 7 by 7 grids, and you have 2 bounding boxes generated and the number of classes are 20. So number of predicted values by this algorithm will be S into 5 into 2 plus 20, which will be around 1470 predictions will be done by this model. So when we are making predictions across different classes, you can see here that in this box you had 3 predicted feature maps. Those 3 predicted feature maps are generated to have 3 different feature maps. 13 by 13, 26 by 26 and 52 by 52 respectively. Why? Because larger feature maps will detect the small objects, and as I am increasing the feature map dimension here, larger feature maps will detect smaller images and smaller feature maps will detect larger images. Coming to the output bounding boxes, as I told you, based on the formula S by phi b plus k, you will have these many number of predictions as given in this example here, and these many predictions will be sent to NMS so that you will get output as only one bounding box. Coming to the architecture, this is the architecture you can see here, which uses 1 by 1 reduction layers followed by a 3 by 3 convolutional layers to perform the architecture. So you have darknet architecture here, which is nothing but an open source neural network which is used for extracting the features. These are given as input to fully connected layers. After the features are extracted by the darknet, the feature maps are flattened and passed through fully connected layers, and you have an output vector here. In the output, the YOLO output will have bounding boxes, objectness core, as well as the class probability, as we have already discussed. Coming to the full architecture, you can see here you have 3 different scales shown here. Small objects for scale 1, medium objects for scale 2, and large objects at the scale 3. So large objects are detected here, medium objects will be detected here, and small size objects will be detected here. This is the architecture, full architecture of YOLO version 3, and you are using here upsampling and downsampling also. Upsampling will be used to reduce the number of resolutions also, and concatenate will concatenate all the feature maps that are being generated. So this is the end. Thank you all.